Yes. So, the previous class we were discussing most about addition of your pi system with your carbonyl. Okay. We saw that your carbonyl can add to your pi system to form a oxytane, and then we said that the reaction most of the time depends upon your alkene also. If it is an electron rich alkene, then your reactions becomes it's not stereospecific, it doesn't be a stereospecific, and it is also not regiospecific. But on the other hand, if you take an alkene which is electron deficient, then the reaction becomes stereospecific as well as regiospecific, and we found out the reason for that, and we did some examples based on that. Now, today in this class what we will do some that is intramolecular Paterno-Buchi reaction. Previously we were explaining about intermolecular addition to pi system to alkene, which you call as Paterno-Buchi. In this class we will be dealing with intramolecular Paterno-Buchi reaction. So, the idea of doing many examples is basically to understand how important is that reaction, and like it can be used for many synthetic applications. You can make molecules which have like really good applications. That is the idea of making this, seeing lot of examples. So, we will take the first example in this case. Yes, we will take a ketone which has an inbuilt alkene. Okay, have a systems like this. Now, I photolyze this. So, what happens? You know that it goes to SN1, S1, that is your first singlet excited state. Since it is aliphatic ketone, you can see chemistry happening from your singlet, as well as it can undergo an intersystem crossing to give you triplet, right. So, how this triplet radical then looks like? So, I can draw a system. This should be my T1, right. So, what this can do now? What type of an alkene it is? Yeah, if we consider R as a methyl, okay. So, it should be an electron rich alkene, right. So, what chemistry then we are going to expect from this? So, the reaction is not much regiospecific, right. So, can we think about reactions then? If I am getting a radical of I get this type of thing, I can redraw. So, I can write 1, 2, 3, 4, 5, 6. Right. One way is that your O dot can add to your carbon C6, right. That you can think about one possibility. So, if it happens, then what you get? So, I get a system like this. What is this? Yeah, again now you are talking about diradicals. So, you know about now diradical, how it behaves most of the time. You are familiar with this. So, what 1,4 diradical does in this case? It can undergo nice cyclization, right. I can get a product like this. Or you can say in other way, since it is not that much specific, you can say that, sir, my O dot can also add to my carbon 5, right. It can also do this. Then what happens in that case? I get a species like radical like this. Yeah, my O dot is missing, right? My O, yeah, O, yeah. So this is 1,5 diradical. So again, it can easily recombine. No? So you get a type of cyclization. Get a system like this, okay. Or you can symmetrically, if you want, you can write it nicely. Right, other way of looking that molecule. So you can think of getting two products by just intramolecular Paterno-Buchi reaction. Yeah, one methyl group, where that methyl group should be the bridge one. Right? Yes, that's good. So you get, this is the simplest intramolecular Paterno-Buchi reaction. Okay. Now we will take another example and see example where like how we see, I am taking this molecule and fertilizing that in acetone. Okay. In acetone, I am doing the photolysis. So, what you can think about? Yes, it goes to S1, then undergoes an intersystem crossing, that is fine. So, you get a triplet radical. How that looks? S1, I can say ISC. So, gives you O dot fine. So, now I can say 1, 2, 3, 4, 5 and this is 6. So, where you want your reaction to be? You have C5 and you have C4 and you have C6, where you want that O dot to add up or abstract an electron. See, if I am going to take from C5, okay, then I will push this to form me a C4 में radical, right. Other way around, if I go for C4, then I have to make a radical in C5, which you look to be very odd. No? It is not simple. So, in that case, I might get only one product. Okay. So, I might end up with taking from C4. If I get it from C4, then see, so even I can nicely form a okay. So, you can have a methyl here. See, if I do this way, okay, I am going to attach with C4, then I will get a radical here. Okay, that is not you do not want. That is why I just did in C5 and created a radical in C4, that looks to be stable. Fine. You do other way around. If I push this, then I have to push my radical, that is on your double bond, which you do not want. So, this is again what 1,3 diradical. Look at this. It's clear. Okay. See that again I am saying this is the question, this was question again I asked in that previous semester, and this is the only product I got, but unfortunately this is not the product. What happens? Any idea? Huh? Yeah. See, I have used my solvent acetone, okay, and you think about this guy, the excitation of this ketone is same like the excitation of your acetone also. So, acetone can also excite, and once it excites, then it can make a another Paterno-Buchi reaction across your this double bond. So, acetone can react now. So, you can see two types of intramolecular either. One is intramolecular, another is intermolecular. You see both Paterno-Buchi, intra as well as inter. So, do not stop in one product, okay, and see that as because you have acetone, you know acetone can be excited, that can also do an intermolecular. So, it is inter. So, you have an example where you have both intra as well as inter. Any doubt? Okay. This type of compounds you have seen many, I use many of the examples this type of compounds. Okay. See, without double bond we have seen examples. What happens if you have a ketone without this double bond? We have seen nice examples. We have seen alpha cleavage, you have seen one more nice thing. Yeah, you can see nice intramolecular hydrogen abstraction if I do not have a double bond, right, that example. So, if I insert a double bond, then you see what happens, it becomes like a type of Paterno-Buchi. See, this type of cyclization gives you a very good stereo specific product because of the ring cyclization and the rigidity of the system. It gives you a nice one product. So, how you get it? This O dot, okay, you want to, there are two choices here. So, one I can write 2, 3, 4, 5, 6, 7. So, you want to take 1 7 or 1 6? 1 7. See, if I am going to take 1 6 for example, okay, then I am creating a radical in 7 position. So, I can add my 2 and 7 to make a bicyclic system, right. See, that is how you think of it. If I do in other way, it will be a 6 and 5 membered. This will be 6 membered. So, that is much more easier, right. I get a system like this if I do. See, the best thing of this, see, this is the product you get, very fixed epoxide on the top of this thing. Okay, it cannot go in other way around. And if you do if you put lithium aluminum hydride LiH into this, what do you get? You get an alcohol. Like this, like you can end up with a very stereospecific products. You are seeing your Paterno-Buchi reaction. See, these reactions are most of the time are 90%, okay, 90 to 80% yield. So, you have to just take your compound, okay, and just photolyze, just keep it in the apparatus, photolysis apparatus. You end up with this product. Yeah, because of the rigidity of the molecule. Otherwise, the epoxide cannot come otherwise. Okay, if it is a simple molecule which is not going to cyclize, then you do. I will give you one more example where you will understand. Okay, we will take the second example where you can really understand this. Okay, I am taking another example of the same time. So, this will tell you how your methyl should be when a cyclization of your 2 6 member ring happens, the methyl should be in which way. That will explain you why the stereochemistry of this reaction. So, now if you do this photolysis, yeah, you know that it goes the system. Sorry, I can, it is an extension, it is a natural product. Yes. Now, how you want this? We are pretty well now sure that it should be forming a 6 and 6 member ring. Fine. And your this methyl should be which position? When you have a 2 system, cyclic system. Yeah. See, that is why the formation of epoxy. See, I can always you get a system like this, methyl. So, this is why it fixes up the stereochemistry. When you open up, now I get my epoxide in this direction only. Okay. And then if I put HI, this type of products you get nicely. These are very good examples of Paterno-Buchi. You can think of building up molecules, okay, like same like you do an aldol and you do your Robinson annulations to bring your cyclic systems, right. So, Paterno-Buchi reaction sometimes sometimes people call that it is equivalent to your aldol, Okay, this type of reaction. You can make CC bond formation very easily. You have many examples where Paterno-Buchi reactions are considered to be equivalent to aldol reactions. Okay. Now we will try this example. I want like you guys try without seeing the board. So, it is more about how you visualize the molecules. One, two, three, oxygen. 1, 2, 3. And you can have a methyl here. Okay. 1, 2, 1, 2, 3, 1, 2. Yes, you have a system like this. See, it is a type of a linear molecule, right? They can always bend around. So, you can now write by yourself what is the product you are expecting of. I do the photolysis in presence of methanol, okay, in methanol solvent. I take methanol as a solvent for this to carry out the photolysis. Yeah, you know that it goes to S1, I see that is fine. You get this. Now, how you think, because it has to come to the alkene, right? You are thinking about an intramolecular Paterno-Buchi. Just can you visualize the molecule, that is more important. How you can bend this. One, two, three, and you have it. Right, you can write this in a simple way like this. Now, you can do your addition, how you want to do it, because like I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where you want to do? You want your O dot to add across C11 or C10? C10, because you are going to create a radical isopropyl type of radical secondary, which is much more stable. So, if you do that, then what you get? And I get a radical. Now, what happens? You know that this radical should combine with this radical, right? So, just draw it. So, I get a type of strain 1. Okay. Now, what happens? Any idea? Can I isolate this product, this type of products? So, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What happens? Because you have a solvent methanol, na? So, can it do anything? What do you think methanol can do? Come on, guys. Can I methanol hit here to open this ring? So, I can generate OMe with hydrogen here? Not possible, because just you want to open a ring, right? Just think about like opening a epoxy rod. This I am just opening. I can take my methanol hit here, then I can open up the ring, right? So, if you get, then what you end up with? Can I have my methyl here? Can I get this product? So, finally, if you see the product, it looks nice. The way it has gone, if I do in methanol, that is the product you get. See, you have to, this is how you can make molecules. That is why I am saying, like you have different applications where you can think of. I think the carb numbers are fine, 10 and 10, yes, okay. This type of examples, if you start working on, it tells many good things, okay, to see molecules how they are. Finished? Huh? We will take another good example. Have you ever studied this example? Like you photolyze this, and after that, after photolysis, treat it with palladium just by heating. Your first step is photolysis, okay. Second step, you can do it by palladium in heat. I think you have studied this reaction. What it gives? Huh? If you take this product and if you, yeah, first you do your normal Paterno-Buchi, then think about what you are getting. So, if you do Paterno-Buchi, what you are going to end up? So, if you photolyze, yes, I am doing all these things again for you. I get my O dot. I get a system like this, okay. You call 1, 2, 3, 4, 5 and 6. So, two ways I can think about: O dot attach reacting with my C6, okay, or O dot with my C5, right. If it is with C6, okay, then what you get? Get a type of 6-member ring with your radical and 1,4 diradical, right. C6, yeah, sorry, it should be other way around. I should get this. This is fine. Other way around product, if I go for C5, what do you get? Can you think about that one? That will be little bit interesting. If I take my C5 one, see basically I am writing all the plausible products, okay, and see the possible, I will tell you what is the product it gives finally. If it is C5, okay, I got a 5-member ring, okay, with a radical. This you can get this product. Then you can combine this radical can I get this, right. Now, this is one of the product and you get another product which is in 6-member. If I put palladium to this, the type of aromatization, right, heat, sorry, type of aromatization I am doing. So, what you think of going to end up? So, you can do the same reaction with your 7-member also. 7-member is nice to get instead of 6-member. Yeah. So, you think of some type of aromatization happening. If it is a okay, then if, see same example, if I do with this is 6-member, right. If I do with 7-member, then just think of 7-member instead of 6-member. Okay. So, if it is 7-member, what do you think? I will just give a clue, like if I am doing the same reaction in 7-member. I get this type of product. What is this? You get nice azulines. Okay. See, I have just did an example with the 6-member. Okay. If I start with 7-member, nicely you end up with azulines. Very good synthesis for azulines. So, nothing you have to do. See, mechanistic wise, yes, you have to do radicals and everything, but reaction wise, what you are going to take the 7-member ketone with an alkene. Just you are going to fertilize for 5 hours or 6 hours, you take the product out, then put palladium and heat it, you end up with your azulines. Clear. So, that is why I say Paterno-Buchi has many synthetic utilities. You can take it for making good molecules. Fine. So, I can move, just I am giving an example of 6-member, I can take for 8-member like that, that time you have to do by yourself. 6-member you do not get on aromatization, that type of thing, only if you go for 7-member you end up with azulene. 6-member you get both of the cyclo products, addition products. Once you move to 7-member, yes, you get azulene nicely. Then the whole reaction is dominated only by your 5-member C5 ring. Okay. That becomes the driving force. You get only one product in that case. See, right now I am not confusing you with which is the major product. Okay. Right now I want you to write all the possible products. That is the more important part. Once you know what are the plausible products I can write, then it is nice to figure out at the end which will be the major and this. So, initially if you find out like this is the major, this will not go, and that will create some problem. So, first write down all the possible products. Okay. Then once we see the product and the radical stability, we can keep on deciding which is much more better than other when it forms a reaction. Fine. You see, normally these questions are asked lot of time in CS here, this particular examples. You can see this example. Most of the time what people do is that people never think about this nor-boron system, immediately they do this alpha cleavage and all these things. Okay. So, this type of system is asked. So, I have seen the same example. So, when you do the photolysis of this, yeah, you know S1 because it's type of an aldehyde, so inter-system crossing is allowed. So, that is why I am saying today you are doing intramolecular Paterno-Buchi, you are very clear that this is where the double bond reacts. Otherwise, what happens, you try to pick hydrogen abstraction. Mostly people who know, they try to do hydrogen abstraction very fast. Okay, they will put like 1, 2, 3 gamma hydrogen abstraction and they finish off. So, little bit, and if it is an acetone, yes, you can start thinking about gamma hydrogen abstraction also taking place in the reaction. Same example we have tried with gamma hydrogen abstraction. I did the same example, but that case the double bond was missing. So, be careful when you do. Now, you know because of so you are going to end up this radical front. Now, what happens? These two radicals can recombine. Yeah, it is a very strange type of ring, but just write the product and think how it again breaks up. Making a ring like this, which is like really strange, right? But you can relax it a little bit. So, if I use little bit of any lithium aluminum hydride, because it's type of epoxy, I can cleave it. Yeah, I can end up with an alcohol, because you have nor-boronyl type of alcohols are also important. So, if I use lithium aluminum hydride, what do you think? So, this eventually breaks up epoxy to give you an OH, and other things will be nice. Get a type of reduction. I will be happy if you can think of other products from this as an. I have not given you assignment. I will start giving an assignment. You can think other way around. Can you think about other products in this case? Same thinking about in Paterno-Buchi angle. Not now. You can just work on later. You can get another type of product also in this reaction if you keep on thinking. fine. See, I am picking some examples which are already there in some exams, okay, some competitive exams. I am also taking that examples, so that you can work that also. It will be useful for you when you go for some exams, like mostly like CSAR and other exams, where you get this type of examples a lot. Norborin's type of systems where you haven't, there you get a lot of examples like this. So, I am just taking that type of example some. So, what product you are going to expect in this? Yeah, you get a first, just try to write that diradical. So, once you start writing like this molecule, then this double bond, you know that doesn't eventually come into the picture. Okay, I can forget this double bond now. So, if someone asks what is the major product for this, yeah, you can write two products, fine. What will be the major product? If that question comes, then you have to be a little bit thinking. Na? Yeah, first we try to write both the products and see which will be the major. If I do my C6, I get this one, which is 1, 2, 3, 4 diradical. Right. Other way around, if I want to do okay, 1, 2, 3, 4, 5, 1, 5 diradical. So, I have a system where I have 1, 4 diradical and 1, 5 diradical. So, get this product in this case. This can, yeah, you can, it's just epoxidize a little bit tilted around the method. Yes. So, I can get this type of molecules, right? Yeah, you just add this, then you can just invert your epoxy up and down. So, what you think is which will be dominating product or which will be major? So, I have like 1 and 2, okay, 2 or 1. 1, 2, okay. Guess for 2, why?
Sir, because the 5-member, according to Baldwin's rule, the 5-member, this attack is more facile. Means this 2 pathway is more facile than the 1 pathway. So
Yours?
Sir, in intermediate, both radical are stabilized.
This, yeah, you go with the stability of radical. Na? Yeah, that's good. That's what I want to see. Okay, it's nothing wrong. See, in this case, you go with the radical. Sir, I say that I get a secondary radical, type of tertiary radical, right? Here it is type of a primary radical. So, if I see with respect to radical, this to be much more stable, and it is again a 1,4 diradical which I can cyclize. the one he thinks about Baldwin rules. Okay. That is also possible. Na? So, here only you get like this system. See, right now I just want to get your mind that there are systems like where you can see, in this case 2 is the major product, okay, 1 does not form, but do not worry, those who have with the 1 I will explain you in next class, where we are going to see addition to pi systems, okay, where in detail I will talk about Baldwin's rule. 5 rule 5 is there, which you take only your 5th carbon. So, there are many rules, okay. That time I will take this example and I will discuss you in detail why it happens, but right now it is product 2 which gets it. But we are going to see, because I want to talk the rule, that example. But whatever you said right now, you are thinking is wrong, it is not wrong, that is right. One, 2, 3, 4, 5, 6, 7. Okay, 7 and 7. Yes, what do you think? It happens. You have a ketone. Yes, you can excite it. Yes, when then how many people say it goes Paterno-Buchi reaction? How many people says that it does not go Paterno-Buchi, like intramolecular cycle addition? Get a radical like this. It can be 7, 8 member, that is possible to do a Paterno-Buchi. Why you are so much confused? You cannot do? Huh? Yeah, it's see, that's why it's really possible, and you get one major product in this case, and the product is yeah, draw the product which you know. So, what product I can draw? Can you draw the product Paterno-Buchi? That is what I say. Please draw the product. Are you going to draw like this? Okay, whatever. Are you going to draw something like this? Now, if you want to draw Paterno-Buchi, right? Yeah, this is our same, others are same. Something you want to draw like this. Are you sure? Or can I say that after doing this reaction, okay, I get only this product. Which you think will be the right? Sir, it forms like this, then breaks up, or it forms directly like this? Nice example to discuss. So, if we are going to do Paterno-Buchi, I should get product like this, right? Then you think this is a stain type of ring, that is why I am going to cleave one of this bond and get my hydrogen, then it abstracts hydrogen from the solvent to give me the product, or nicer it will go like this, then it will abstract an hydrogen. I am not going to make this ring. Any idea? So, it is a very good example in that sense. Can you give a thought about this? In next class, can we discuss on this part? Can you come out and tell us, sir, this goes only this way? Or you can come out with some other product also and tell me this is a product, I think it is feasible. It is a very good system in that to do a Paterno-Buchi. Yeah. I have a ketone with an alkene. This is 7 membered, this can be 7 or 8, whatever it is. Can you think about the right product? Fine. So, I will just finish off with some words. So, we have seen carbonyl chemistry, we have discussed completely about alpha cleavage, cleavage reactions, then we discussed about hydrogen abstraction reactions, and then we discussed about addition to pi system. Okay. Next class, that is in 1 hour, I will be covering you the next 2 reactions, which are simple, that is energy transfer and electron transfer reactions. Okay. Once that is over, then we are finished with our n-pi star reactivity, then we will go to pi star reactivity. Okay. So, with n-pi star reactivity, then we have an exam based on n-pi star reactivity. Fine. So, with that we will end this class.